Everyone, welcome to another GDG AI for Science event. Very excited for today, learning the language of wearable sensors with SensorLM. So I'd like to welcome Assistant Professor of Computational Medicine from UCLA, Yuzhe Yang, and I believe we've got a Ph.D. from MIT and currently a visiting faculty researcher at Google. So I'll hand over to you to get into the technical stuff. Thank you.
Sure, yeah. Thanks for the invitation, and yeah, it's a pleasure to be here to just share with you our latest work. So just want to make sure the level of my voice is good for everyone. Okay, sounds great. So I'll just great. So I'll just get started. So just to motivate things a little bit today. We all agree that we're joining in sensor data. So one of the most ubiquitous sensors is our smartwatch or wearable, which can basically continuously and accurately capture our vitals, such as your heart rate, your respiration, your blood pressure, and even oxygen saturation. So this is really exciting because more than 0.5 billion people on Earth hold a smartphone or a wearable. And if we deploy such sensing capability, it can be also called universally accessible and also enable this in-home, continuous, and longitudinal screening or health triage. However, it is still far from being scalable or intelligent because although we're drowning in the sensor data, I would say we starve for insights from them. So what do I mean by starving for insights? Let's take a look at one sensor data example. So traditional sensor analysis requires domain experts to interpret patterns. And here I show a daily multi-channel sensor dataset, and this x-axis is time. I want to make sure I have my pointer here. Yeah, and I want to. So this x-axis is time. You see from midnight to noon to another midnight, and here each row is a specific sensor feature derived from the wearable, such as your heart rate from your PVG sensor and your steps from your accelerometer sensor, etc. And as you can see, this wearable captures our physiology and behavior continuously. And while this raw signal are hard to understand, imagine it will be really useful if we can turn this into meaningful human interpretations about our sleep, for example, here and here, or activities, for example, here you see some increase in the accelerometer here, or even some anomaly events such as here, or here.
Sorry, Yuzhe, I can't see your cursor.
Oh, I see. Let's see.
Okay,
can you see? Can you see now?
Maybe
still no.
Hover it over the meet window, or over the actual. Oh yeah, I can see that. There we go.
Okay. Yeah, but either way, like it's not that important. So I'll just continue. So basically, what if we can turn this into some meaningful human interpretations, about our sleep, for example, around the midnight, or about our activity, for example, within morning and afternoon, or even some anomaly events where your sensor readings show spikes. And in fact, this is pretty crucial for user engagement, for example, gathering health insights, and it can potentially also do interventions. So the question here we ask is, how do we interpret this sensor data? And can we actually make this sensor data interpretable or sensor data interpretation as readable as a news article in natural language. So let's imagine. I like to draw an analogy to computer vision systems. So, we can describe the scene or the context in an image with natural language. And what if we could translate this raw numerical sensor stream or sensor readings into clear descriptions, such as here, we can report the statistics of your metrics and also identify unusual patterns in your readings, while also generating events with their associated time periods. So that's a North Star we would like to achieve. However, there's still a few key challenges that prevent us from understanding or connecting sensors via language. So first of all, we're interested in these longitudinal sensor readings, such as your daily or weekly data, which contain more important information about human health. And you can see these sensor data are pretty high dimensional and continuous. And they're pretty hard to interpret directly. And even state-of-the-art LLMs fail on this raw sensor input. For example, the first thing we did is we directly input this sensor data into state-of-the-art LLMs, such as Gemini, and ask it to do zero-shot reasoning on activity recognition or description generation. So we restrict these activity classes into 20 labels and also provide this so-called in-context example for Gemini reasoning. For example, we provide like pair data with the sensor and the actual activity as few examples in the prompt. However, the resulting AUC or accuracy, basically this is an accuracy measure, is 0.51 on activity classification. So for those who are familiar with this metric, or this like macro AUC, it is basically random guess. Okay, and then we ask it to generate descriptions for sensor data about statistics, trends, or events. And we further compare it with the actual ground truth reported by the user. And this I will show an actual example later in this talk. But you can see, as you can imagine, the generated descriptions are incorrect, or like in most cases incorrect, for both the events, the event type, or the associated time periods. So this indicates that current LLMs cannot directly interpret such dense and continuous sensor data. And in addition, to develop such foundation models or multi-model large models, we need these paired sensor text data. However, there is no such large-scale sensor language datasets in the first place. So this motivates us to develop this new work called SensorLM. So in this work, we kind of propose a new family of foundation models called sensor language models. So given an input wearable sensor streams, here we consider the 24 hours data, basically daily data. We further design an automated way to create description text or captions for sensor data at scale. And this actually leads to the largest sensor language dataset to date. And the exact pipeline, I will describe them in a sec. And based on this largest dataset, we develop a flexible multi-model pre-training architecture for SensorLM. And when I say flexible, it means it can represent or recover a few representative pre-training architecture currently in the literature. And this architecture kind of connects the sensor with text via a contrastive loss, while also we're able to generate the sensor readings or sensor report based on a text decoder with a captioning loss. And I will detail the actual architecture later in the talk. So by this design, what I mean by flexible is it actually enables very interesting capabilities. So first of all, once we have a sensor encoder and text encoder, we can enable zero-shot sensor understanding via free text input. You can also retrieve sensor data, you can also do sensor text retrieval and alignment in a zero-shot manner based on a database of sensor or based on a database of text. And crucially, this SensorLM provides a pretty good representation for few-shot adaptation with limited labels. And it can also support sensor caption generation in a zero-shot manner. And I kind of show here a performance overview of our model compared to state-of-the-art LLMs such as Gemini and Gemma, as well as state-of-the-art self-supervised learning algorithms such as SimQueer or Dino. So it's a little bit small here, but different colors here shows basically different type of evaluation protocols such as zero-shot evaluation, few-shot evaluation, or retrieval. And we also show like there are many tasks we evaluate on, such as classifying activity, anxiety prediction, hypertension prediction, etc. So compared to all these state-of-the-art methods, we can see SensorLM achieve on par or better performance and is consistently performing well across different tasks and domains. So this is a very high-level overview. So the question to develop the model, the first question we ask is how to describe sensor data. Okay. So we actually propose this pipeline, what we refer to as a hierarchical sensor caption generation. By the way, feel free to raise your hand or ask questions in the interim. Let's make this as a more like an interactive session. So we basically designed this caption as a hierarchy, and we define 3 levels of granularity. And here, we basically show a simplified version of the sensor input where we show 3 channels, like your heart rate, accelerometer data, and temperature, and the x-axis is the time. So first of all, the first level, what we refer to is the statistical caption, where this simply calculate the basic statistics, such as the average, the standard deviation, and also the minimum or maximum value to identify outliers for each of the sensor readings. And here you can see some examples for heart rate or accelerometer descriptions. And on top of this, we further define what we refer to as pattern or trend description. For example, in these red boxes, you can see the heart rate actually has a spike here, which we probably want to mention or describe as it might experience in some event here. And also for accelerometer or temperature data, you can see the decreasing trend over certain periods, which we also want to highlight. So the second level, we name it as structural caption, where it describes basically the patterns and trends for different sensor channels. And here are some examples you can see as a peak heart rate is detected at minute blah, blah, blah. And from minute this to this, the accelerometer data exhibits a decreasing trend. And finally, users or consumers might label their events or activity during their usage of their smartwatch. For example, in the first few hours, the person is sleeping, and in this period marked by this gray box, person is experiencing an elliptical event or training. So based on this higher level description or contextualized information, we define the third level as the semantic caption, where we capture the contextual meaning of the sensor data, such as your activities, your sleep, your mood, etc. And here are some examples basically illustrate this. Your sleep took place during minute 5 through 400, and there's an elliptical episode occurred between this period. And during training, we simply combine all these descriptions together to form a kind of sensor caption or sensor report for the daily wearable data. And by this method, we were able to present the largest sensor text study to date. So we leveraged the internal Google data collected via different smartwatches, such as your Pixel phone or Fitbit. And in total, we collected over 2.5 million person days from more than 100K people. And this results in a pretty large pre-training set consisting of 60 million hours of sensor data across more than 100 countries. And to compare with the current or like the existing sensor text study, you can see that not only we have orders of magnitude larger number of samples, we also contain more sensor channels as well as more a more complete or comprehensive summary of the text. Okay, so once we have this large-scale data set, we kind of design our SensorLM model architecture as follows. So first of all, we have a sensor encoder to encode. Yeah, go ahead.
Yes, thank. Quick question on, could you explain how did you generate the label? Is that like a human generating the labels?
Yeah, so are you referring to this semantic part? Or the...
Yeah, so semantic part, yeah, that's right.
Okay, yeah, so yeah, that's a good question. So this is the kind of like the noisy ground truth we have from the wearable data, because for example, some watches, they have this automatic algorithm that can detect whether you're performing some activity or not. And users can also log their activity in the data. So we kind of like using this noisy labels as the semantic information to fuse into the caption. And we don't have post processing of those labels, so we just use whatever we have. Does that answer your question?
Yeah, makes sense. Thanks.
Okay. Okay. So once we have this data set, we kind of design our architecture as follows. So we have a sensor. So first of all, we have a sensor encoder to first patch this sensor data and then encode it into embeddings. And we also have a text encoder similar to what LLMs use to encode the caption into the some text embeddings. And on first level, we have this contrastive loss, which is obviously not designed by ourselves, but it's a pretty mature machine learning technique which aligns the paired multimodal data and repel the unpaired data. So the first level, we have this contrastive loss to kind of like align sensor embeddings with the text embeddings. And on top of this, we further add a multimodal text decoder inspired by the previous work called COCA, where we kind of like conditioned on the sensor encoder, sensor embeddings using the cross attention, and train this multimodal text encoder in an autoregressive manner to generate the caption. So this gives the model the generative capability for natural language output. And we have this captioning loss also, which is a very standard autoregressive loss. So I earlier mentioned this is a pretty flexible framework, and it turns out that we can have different weight for these two losses so that it can recover different training mechanisms, and we also have some implications for our actual performance for different purposes. For example, for those who are pretty familiar with CLEEP, which is a very well-known method to align the images or vision with language. So if you set the caption weight to 0, the training mechanism directly recovers CLEEP. And similarly, if you just set the contrastive loss weight to 0, the training mechanism recover another method called cap, which is basically trying to generate captions based on visual data. And if you combine both losses in an equal weight, it recovers previous work that trying to combine this contrastive and generative method called COCA. And in our evaluation study, we actually find if you further tune the weight for different losses, you can actually get a pretty nice trade-off between certain capabilities. For example, whether you want better discriminative capabilities of imbalance versus you want higher quality generation of the text. Yes?
Sorry, another quick question on the sensor encoder. Is that like based on VIT?
Yes, it is based on VIT. Yes.
Okay, thanks.
So, any other questions on the model part? Okay, just move on. So, so our pre-training strategy, we basically fixed a equal weight between the two losses. But in our paper, we actually showed an ablation study on how you can tune the weights for different losses, and that will help you achieve better performance in different capabilities. So the evaluation setup for SensorLM is relatively straightforward, I'll say. So in this paper, we only consider 2 major tasks. The first one is activity recognition, and the second one is health condition predictions, such as hypertension and anxiety. So to evaluate both of these tasks, we select this unseen or like out of distribution activity dataset, which is sampled from completely new participants from our pre-training set. And in total, we have more than 30 classes of activities labeled as ground truth. And for the health prediction task, we also have another cohort study, which we refer to as the metabolic dataset. And they have self-reported outcomes for hypertension and anxiety. Basically, they have the questionnaire at the beginning of the wearable study, and we continuously collect the data for around 1 week, and we assume, and we just treat the question, the noise label from the questionnaire as the ground truth. And to evaluate SensorLM, as I just mentioned earlier, because there are many capabilities the model can do, so we evaluate both the zero-shot prediction and the few-shot learning for the model. And on top of this, we also have this zero-shot sensor text retrieval task, as well as the zero-shot sensor caption generation, and qualitatively compare with the ground truth. As for the baselines, for zero-shot tasks, we mainly use the existing state-of-the-art LLMs, such as Gemini, Gemma, etc. And for few-shot tasks, we compare to existing self-supervised learning baselines such as Sinclair and Dino. Okay, so the first or the most interesting capability of sensor language models is its zero-shot prediction capability. That is, we can classify and understand new sensor data without training. And more specifically, how we evaluate this is once we have a new sensor data, we can input textual descriptions. For example, the person is biking or the person is not biking. And then we can get the output probability for these two events or for these two descriptions based on the cosine similarity of the sensor embedding and each text embedding. And then we will be able to directly predict whether there's a biking event in the sensor data. So we compare SensorLM. Okay, so each row, each column here is actually a different task. So we both test on the 20 class activity classification, as well as also abstract some higher level contextual information classification. For example, the second one is the environmental context classification, where we have this different context, such as whether you're in the water or you're on the land, whether you're outdoor versus you're indoor. And further, we also have some fine-grained classification on top of this 20 class. For example, we have this gym cardio class in general for the activity, but within that gym cardio superclass, we further define 4 to 5 fine-grained classes to test the fine-grained recognition capability for these zero-shot methods. And across all these evaluation tasks, we can see SensorLM consistently outperforms this general purpose LLMs such as Gemma and Gemini. So the second capability I would like to highlight is this zero-shot sensor and text retrieval and vice versa. So for sensor to text retrieval, it is, okay, so given a sensor data segment and give a text database, for example, 1,000 or 10,000 text descriptions, can retrieve the correct one and give similarity or ordering for all other text captions and vice versa. For example, if we want to do the text to sensor retrieval, like we given a query caption, such as this is we want to search an individual with sleep apnea, and can we find in the sensor database like which is the correct sensor data? And based on this zero-shot capability, we're able to calculate the probabilities or the cosine similarities between these pairs, and we're able to retrieve the highest one. So, so first, qualitatively, I would like to show one example here. As you can see, it's again like a simplified version for wearable data, and the x-axis is the time, and the y-axis is so the rows are basically 3 selected channels, such as heart rate, accelerometer data, and temperature. And here are 3 events labeled by the user ground truth, which is in the first few hours, the user is sleeping, and then he gets up and did some treadmill, followed by a strength training period. And now I'd like to show 4 representative captions out from like 10K caption database. So the ground truth here is, you see that there's like a run period and there's a treadmill period recorded between this range, and there's a strength training noted, and a sleep took place between like minute 0 through 300-ish. And there are also pretty similar captions where you probably had a very similar concept of the event, like walk versus run, and also a very similar period of that event. For example, highlighted by yellow here, the period time is not exactly the same, but they overlap pretty much. And you can have this like another similar caption where you correctly identify all the events, but you fail to localize them. And there's another very dissimilar caption where you basically incorrectly identify both the event and the period. And interestingly, we're able to generate this similarity score using SensorLM. And first of all, we're able to retrieve the ground truth, and the similarity score actually gives you some semantic information about what the model is actually learning. So it's learning both the event information as well as when did the event happen. So I see one question in the pause. So is the prediction better for activities where there was more data for, or are the different predicted categories just have similar modality measures? I think, yeah, this is a good question. So I'll say in general, of course, if you have more noisy labels or concepts for those, head classes in your pre-training set, then in general, the performance will be better compared to tail classes. But to your second part of the question, there's some interesting analysis I will show later in the talk that the power of this sensor language model is it can generalize to unseen concepts, and by leveraging the language semantics. So this is one qualitative example for this cross-modal retrieval. And quantitatively, we also measure the retrieve at 1 and retrieve at 5 accuracy over a set of 100 samples or like 5,000 samples. So quantitatively, SensorLM performs very good compared to existing, like LLMs such as Gemini or Gemma. And I would like to highlight here, you see there are many dashes here, which indicates the task is not even feasible. So this is because once you increase the retrieval database, for example, you want to retrieve from 5,000 samples to retrieve the correct description, or even like from 10K samples, LLMs has this inherent context length limitations. And even if you do like a multi-turn conversation, it will easily forget what it will earlier see, especially for the sensor data. So this is an inherent drawback that LLMs cannot do this. Okay, so moving on. Another interesting capability is, can we efficiently adapt to certain tasks or like do this task-specific fine-tuning just using very few samples? So here, you want to show that SensorLM actually provides better sensor embeddings for tasks with very little label data. So we do this linear probing or linear fine-tuning on 3 different tasks. The first 2 are the health prediction tasks, such as hypertension and anxiety prediction. And the third one is the 20-class activity prediction. So the x-axis or the columns here are the number of samples per class. And hypertension is just 2 classes, binary classification, hypertension versus no hypertension. And same for the anxiety one. So as you can see here, by just adding tens of samples and tuning on this very small set, we're able to achieve on par or better performance compared to state-of-the-art self-supervised methods such as SimClear or Dino. And this trend is pretty consistent across all these different domains. And if you take a closer look, for example, on the 20 class activity classification, you'll see this this linear probing for SimClear, their confusion matrix is actually looks not that good, and many samples are confused to these two classes like skiing or kayaking. In comparison, our model, by just tuning on a few samples, we're able to achieve this pretty nice diagonal distribution where you can correctly classify most of the activities with more than 70 or 80% accuracy. Okay, and finally, one interesting capability of SensorLM is by using this text decoder, we can generate a sensor caption or sensor report in a zero-shot manner. And what I mean here is you can just input a new sensor data and give a start token to the text encoder, and we'll be able to automatically generate a caption or a report for the sensor data. So, for example, here I'm just showing one specific example with a limited time context window, but for all evaluations, we're taking daily data. For example, here within this range, there are 2 biking events happening around 3 p.m. and there's the person goes to bed at around 12 a.m. So the ground truth caption we'll generate for this is, okay, there are 2 bike events detected between this period, and there's 1 sleep event detected between this period. This is the ground truth. And we directly input this to Gemini. And as you can see from the caption generated by Gemini, so first of all, there's one misidentification of the event, and it does not identify the biking events, but rather it outputs there's some periods of walk identified between certain time intervals, and there's a sleep detected at the end. And in contrast, for SensorLM, we're able to identify the biking event, although there's will also be some inconsistent generation for other events such as walking period detected on this, but you can actually see the localization is also pretty clear and pretty close to the ground truth. For example, it shows like 873 here, and this is also 872. Okay, so in addition to these interesting capabilities achieved by this model, I'd also like to highlight, also related to the question in the chat, that by using this multi-modal model like sensor and language, we're able to generalize to unseen concepts unseen concepts or like classes in the pre-training or either fine-tuning. So in our pre-training set, there are actually more than 50 plus or like 60 plus activities, and we exclude the tails and basically just preserve the head classes or head annotation in our text description, and we explicitly include all this activity from the pre-training set. And interestingly, we're able to still achieve pretty good performance compared to existing LLMs, and some are pretty good as you can achieve 0.8 AUC. And when we take a closer look to their semantic embedding space, both for the sensor embeddings and text embeddings, and here we just highlight 2 pairs of activities, very interesting pairs of activities. One is snowboarding and skiing, and another is Pilates and yoga. So you can see, although we never see snowboarding in any of our caption, or we never see yoga in any of our caption during training, the model is able to use the inherent language semantics to have this very similar text embeddings between snowboarding and skiing, as well as between Pilates and yoga. And this will translate to this multi-model integration on the sensor part, where you kind of like have very similar embeddings between this pairs of activities. And finally, one thing we like to highlight is the scaling loss. So we also investigate whether when we scale up, can this performance keep increasing? So a little bit background about scaling loss. So this is so in natural language processing, this is first observed by OpenAI that if they increase compute or data size, or even the number of parameters of the models, they see a pretty good linear relationship of their task loss in the log space. And because we don't have this loss as a good proxy, we instead use this zero-shot activity classification AUC as the measure. And when we scale up our compute, our data size, and model size, we also observe this scaling effects. Although the slope is a little bit decreasing when we further scale up to the region, but it doesn't hit a plateau. So what's the implication? So basically, although like we are using a pretty large pre-training set containing more than 60 million hours of sensor data, that is still relatively small part. As you can imagine, we are actually collecting this data every day. So it tells us that we can still scale up and get better and better performance with more data and more high quality labels and larger model sizes. So this potential is really like unlimited. Okay, so before I conclude this talk, I would also like to highlight some ongoing work that we're doing. So our team has also been building this large sensor model, which is a uni-model foundation model for sensor data. And the benefits of building such a model is it can also tackle this sensor missingness issue, where, for example, in daily readings, because of the sensor detachment, probably you'll experience many structured missingness in your sensor data. And here we are proposing a method, a foundation model that is also able to generate or impute the missing data. And building on these foundation models like SensorLM and this LSM models, we also have these personal health agents where we have this interactive chatbot where you can actually ask any questions, ask about your health data, and have the agent to do code generation, to use the tools such as calling SensorLM or LSM, and doing this multi-step reasoning to finally give you feedback and to maintain a dialogue between with the user. So this has a better management of your health data and in a more interactive way. And really, before I end, I also want to shout out to my lab at UCLA. So we are a group of researchers focusing on AI for healthcare, and I direct this health intelligence lab. And in our lab, we also do research about fundamentally how can we improve medical diagnosis and health sciences, such as early diagnosis, medication response, and monitor these sleep behaviors and give you fair deployment when we actually deploy these models in the wild. So again, very happy to collaborate, and we are open to any collaboration requests, and happy to help and shape this AI for health future together. Okay, so that's all for this talk, and thank you very much. I'm happy to take any questions.
That was really fascinating. Thank you so much for that. I had one question. So I'm relatively new to getting a Fitbit, and when I set it up, it said like, "Would you like to be included in trials or clinical trials?" Is that sort of how you participants? But that scale of the amount of people that you had on board is huge.
I cannot fully speak of that, but my guess is probably it is one of the trial that Google or like Google Health is conducting. So I think within Google, they basically have some specific design cohort where they have like very limited individuals, and they can collect they will send out their wearable devices, and they will ask the users to wear it. And at the same time, they can collect some labels such as their demographic information, or like send some like questionnaires for some medical histories. So those will serve as pretty useful labels, for example, for the SensorLM development. So I would say probably yes, but I cannot fully speak of that.
Good stuff. All right, there's a very burning question from Scott in the chat. What's the plan for SensorLM? Will it eventually be available for external use? The models coming out?
Yeah, very good question. So this is the V1 version of SensorLM, and for the next step, so currently our team is working on a public version where we hope to release the model and the checkpoint and the code and part of the data where the IRB permits us to release very soon. So keep an eye on that. And regarding the next version of SensorLM, as we just mentioned, there are also, so for this specific paper, we're targeting only on activity and certain metabolic health tasks. But there are so many things you can do with the sensor data about, like, for example, understand your sleep, understand your mood, understand other behaviors. So we're trying to extend these domains where we can perform more interesting tasks.
Good to hear. Okay, yeah, a couple more in the chat. I'd like to hear your thoughts on having a cleaner but smaller data set that in theory would perform better because it has less noise versus using more but noisy data if the data you'll be predicting for has fewer modalities and is noisy. So yeah, I guess what's the trade-off? Yep.
Yes, very good question. I think you hit the point. I totally agree with this. Of course, any training of foundation models or large models is about data. People just saying like garbage in, garbage out, right? So unfortunately, like for us at this scale, it's a little bit hard to verify the data quality, especially for the specifically for those like semantic labels. So as a result, like we don't do that manually, unfortunately. And for pre-training, what I've been mentioning is we use these noisy labels. So I would rather refer to them as noise labels. But one thing is, if you want to adapt to your downstream tasks for specific tasks, you can actually collect very limited data set, but with high quality labels. And you can adapt this foundation model to that specific data set with high quality labels. And that will ensure better performance for the specific task. So I think that's the general strategy, like, especially in the sensor domain.
Stuff. Okay, another one. Any thoughts on how would this approach compare to using a simple supervised classification, for example, for activity detection? Any pros and cons of each?
Yes, very good question. So I believe in our paper, we should have some results compared to supervised baselines. So basically, you can achieve pretty good performance on par with supervised baselines. And I would highlight that a good thing about foundation model is adaptability, especially for SensorLM, because it's zero shot. We can actually perform 20 tasks or 50 class activity classification without tuning. So I think in product currently, because you want to ensure the performance, typically you just restrict your activity labels to certain number of, for example, like 10 or 20. And you have specific models specifically tuned for that activity. But if you have one model that can adapt to many downstream tasks, that would be a game changer, I would say. Yeah.
Stuff. And Amit says, I love this. Thanks for sharing. And are there any plans to use it for predicting falls in the elderly?
Well, thanks for your comments. And you kind of like predicted our like team roadmap. I'll say yes. There's definitely like interest in like home usage, especially like identifying as you said, like falls for elders. I think related to the point I just mentioned, we also need some to make this possible. Like you, of course, like you can use zero shot, zero shot capability of this model directly. But if there's not many events that associated with falls in the pre-training set, the performance may not be that good. So if you can have like a very limited, you can just collect a very small but high quality fall detection data set, then you can easily adapt the model to identify falls. So I would say it's pretty straightforward to extend to that.
One more question came through. Can the model analyze other types of data, for example, spectroscopy, etc., or is it focused only on time series?
Well, that's a great question. So I would say yes, in the sense that the model or the captioning strategy is relatively the model and the captioning strategy is broadly applicable. So you just need to adapt to your own context. For example, if I go back to this this sensor caption slide, you'll see basically how we describe this sensor data is like we have this human prior that we wanna understand these three properties. And for the training the training method is also broadly applicable. So I would say, although the method right now is just for sensor time series, the principle behind this either like the captioning or the modal detection should be broadly applicable. Yeah, okay. I just saw like you said, can you provide some examples? So I would say like one interesting example is apart from sensor data, there's like audio data, for example. For audio data, usually like people will transform them into spectrogram, and you want to do some like audio event detection or like audio to speech translation, and this is also like a perfect scenario where how you want to caption the audio like based on like background noise or like what are the sound for different classes and what is the actual word the person is speaking. So I would say like this, although like current method is focusing on wearables, but the principle should be extended. Yeah.
Bruno, do you want to ask yours?
Yeah, I have a few, so I thought it'd be easier to ask. Thank you for a nice talk. I noticed a lot of your evaluation was on a proprietary data set, and you compare mainly to things like Gemini or Gemma that were not specifically trained or pre-trained to address the sensing challenge, the human activity recognition. Have you guys done any evaluation on existing data sets in literature or comparison against work? I think I saw Flora Salim. She's done quite a bit of work in this space. How does the SensorLM model perform compared to related literature?
Yes. Right now we haven't so I guess when you say related literature, you're specifically referring to those doing like sensor data understanding, right?
Yeah.
So right now, in the paper, we actually implement one method for also like for zero-shot sensor data understanding, and we direct compare to it, and it performs pretty good. But all the evaluations are done on our data set, partly because some non-technical issues, like it's hard to onboard public data sets to Google Server, for example, and so the evaluation hasn't been very comprehensively done for all the public data sets. But once we have the public version, it should be relatively easy to test it for different public data sets.
Yeah, it's just I came across a few similar, transformer-based algorithms that kind of operate in that 80-90% range. So it will be interesting to see the comparison. But the more interesting question I have is around the scalability of the data. So it's quite exciting to see that you haven't hit the limit. What's your thoughts on scaling up? And by that I mean a couple orders of magnitude maybe of actually getting data sets annotated. So probably self-reporting by people doesn't work anymore. So where do you take it from here to get to that 95-99% accuracy across a wider range of activities?
Yeah, that's a great question. So right now, because I don't have the actual results, so it's just my hypothesis. But I think there's two interesting aspects we should consider. First one is the data diversity. So if you just increase the volume, but the mutual information between the new data and your old data is very high, then you're effectively not increasing that much information in your pre-training data. And that also relates to how you select your population. Is it just like teenagers, or like it contains more like elders, or like it's balanced across all demographics? So increase the data diversity, I would say it's more important by compared to blindly increase the number of participants. And second one is, as you mentioned, the label diversity. So right now our pre-training set is mainly about daily activity, and those are crowdsourced by consumers. And in the same time, we try to conduct more studies or collect data from specific domain studies, such as, for example, mood, depression, sleep, etc. And when we have more of this like diversified labels, I think the generative capability or the discriminative capability of the model will be more interesting.
Cool, thanks.
All right, I think we're at time. So thank you everyone for joining, and thanks very much, Professor Yang. So we'll see you again soon and next time.
Yeah, thanks everyone. Feel free to reach out if you have more questions.
Thank you.
Thanks. Bye-bye.